Hello everyone, welcome to another lecture series on measure theoretic probability. So today on lecture 9, we will be talking about the continuity of probability. We're supposed to talk about this in lecture 8, but time didn't actually permit. So we talk further about the independence of events and the independence of some classes and the sigma field generated by those classes. So today we talk about the continuity of probability. So there will be some notations you have to note down. And so if you have events an and a, which is a subset of omega for some indices, then by an with the arrow up to a, that is an approaching a from below to a, then we mean that the ans are subset of each other. And if you take the countable union of these ans, is equal to what? A. If you have an approaching a from above, we mean that the ans are supersets of each other, and the countable intersection of the ans equal to what? A. Okay, so now we talk about the continuity of probability. So a theorem. So let P be a probability measure defined on a field. Then 1. What do we mean by continuity from below? If an and a lie in the field and an is approaching a from below, then the limit of the probability of an, that's the limit as n approaches infinity of the probability of an, is equal to what? The probability of what? A. Okay. And 2. Continuity from above. If you have an and a lying in F and an approaches a from above, then the probability of an approaches probability of a from above as well. Okay, so 3. Countable subadditivity. If you have a1, a2 through to infinity, and the countable union of these a case lie in F, the a case need not to be disjoint, then the probability of their countable union is less or equal to the countable sum of their individual probabilities. Alright, so we are going to prove 1, 2, and 3. So proof of 1. For 1, since we have the a case up, since the ans are approaching a from below, then we need to create some kind of disjointness because the ans are subsets of each other, and we are going to create some kind of disjointness in the ans. And note at the end, the countable union of the b case will be equal to the countable union of what? Of the a case. Note, these disjointness, the b case are disjoints, and the a equals to what? The countable union of what? Of the b case. So we pick some finite aspect of it, and we let an to be equal to what? The finite union of what? Of this bk. This will be useful in our proof. Note that the b case are disjoints. So the probability of a is equal to the probability of what? Their countable union. And by the third axiom of probability, we know that this could be what? The sum of their individual what? Probabilities. And we take limit as n approaches what? Infinity. So this infinity, we take n to what? To approach what? Infinity of the sum of the individual probabilities of the a case. And we can rewrite this back as we did here. So this will be the limit as n approaches infinity of the probabilities of their finite unions of the a case. Note, this represents what? An. So we bring the an back. So now probability of a is equal to the limit as n approaches infinity of the probabilities of an. So 2 follows from what? 1. Just by the idea of 1, we do same. Since using part 1, if you have the an approaching a from above, then if you take the complement of an, then the an's complement to approach a from what? Will approach a complement from below. Then by the idea from 1, we prove this. So we have 1 minus probability of an approaching what? Approaching from below, 1 minus what? The probability of what? A. So this implies that the probability of what? An approaches from what? Approaches from above to a, the probability of what? A. So we are done with the proof. We just use the idea of 1 to prove this. What do you mean by countable subadditivity? So since you have countable subadditivity, we're going to use the idea from finite subadditivity to prove the countable subadditivity. Note, if you have events A1 through to AN, then the probability of the countable union of the finite unions of the AKs is less or equal to the finite sum of their individual probabilities. So now we take limit and take n to infinity, then we are done with the proof. It just follows suit as we did early on. So you just take n to infinity and it follows suit. So here will be replaced by infinity, here to be replaced by infinity, then we are done with the third proof, that is the countable subadditivity property. All right, now there are notations we need to actually note down. Okay, so for a sequence of sets A1 through to infinity, then what do you mean by the lim sup of the events or the sets? So the lim sup of the sets are the countable intersection and countable unions of what? Of these AKs. And the lim inf of the events are the countable union and countable intersections of what? Of these AKs. Note that all of these are events. All right. So if you have F, which is a sigma field that contains these sets for which you took countable union and countable intersections of, then it implies that the lim sup and lim inf also belongs to what? To F. Okay. Since these are events, the countable union and countable intersection of sets also is a set. If you have any elements belonging to F, what do you mean? So if omega, small omega, belongs to the lim sup of AN, if and only if for any n there exists a k that is greater than n, such that if you have that element such that you have the element belonging to what? That AK. This implies that you're going to have that element is in one of the AKs infinitely what? Often. You're going to see that element infinitely often as you take the countable intersection and countable unions of what? Of this AK. You're going to see that elements in it infinitely often. All right. Similarly, if you have an element belonging to the lim inf, if and only if there is an n such that for all k greater than n, we have the element belonging to what? That AK. Thus, you're going to see the element is in all but finitely many of what? Of the AKs. All right. So this is what we mean that an element belonging to the lim inf of AN. All right. Something you have to note. The lim inf of AN is always a subset of the lim sup of what? Of AN. All right. Thank you and see you again. All right. Have a good day.